protein structures that are predicted by AlphaFold in areas which they have low model confidence, areas where AlphaFold itself is not very confident about them, would they change dramatically under molecular dynamic simulations? Or would they, are they very unstable under molecular dynamic simulations? And I was digging into this where AlphaFold itself says that, uh, you know, regions that have pLDDT less than 50 is a reasonably strong predictor of disorder, and which means that they should ideally be very unstable under molecular dynamic simulation. And so to test that out, what I'm going to do today is I'm going to select a protein. Uh, I have just selected E. coli here in the AlphaFold protein structure database, and I've chosen proteins that have a very low range, as you can see here. And I'm just going to choose this first one. So if you can see, this is a protein which is ideal for our use case. It's got a center uh, which is reasonably high under AlphaFold pLDT prediction, and you've got areas which are reasonably low. So let me just download this PDB file. Okay, and let's see how it looks like. Yeah, this is a typical AlphaFold file. And let me just go to MDSim 360. It's a completely online platform where I can go from PDB to GROMACS in a few clicks. So I'm just going to log in. I already have created an account, so I'll just log in here. Okay, perfect. So I'll create a new job and I'll select protein in water because I want to see how stable this specific protein is. I'm going to upload the PDB file that we downloaded from AlphaFold database. I'm going to choose this file specifically. It was this one. Let me click this. Perfect. And just so that I have reference for what this specific simulation is, I'm going to update the job name also. Do that. Okay, perfect. Let me prepare the input now. So now the file has gone back to our servers and we're doing a lot of sanity checks. And this is the PDB file. This is how the structure looks like. I'm just going to, there's a single protein chain, but still I'm just going to select it. I'll click submit. And for the purposes of this simulation, I'm just going to select CHAN36, but if you want, you can change it to Amber or OPLS. Depends on what you want to do. And let me click submit. So this is going to perform the PBC setup, which is going to include creating the GRO files, the TIP files, the topology files, and whatnot. Okay, great. So now the next step would be to solvate the model. And I'll just choose octahedron because this seems fairly compact. Edge distance of 1 is fine. Let me click submit. Okay, great. So it has created a water, it's added water and solvated the simulation. And let me hide water. Perfect. So it's created an octahedron around the protein. Excellent. Now I'll add ions to neutralize the model. So let me just add KCl. Actually, no, wait, let me add NaCl. Let me add this. And let me remove KCl. I'll make this neutralizing. So it will add NaCl. Let me click submit. Okay, so it has added NaCl ions, as you can see here, to neutralize the system. So this should be chlorine. Yes, it is. And this thing should be sodium. Okay, great. So now the next step to do is perform state energy minimization. And let me just play with the parameters a bit. Let me increase the convergence criterion. Everything else seems fine. Let me just run this now. Okay, great. So now state energy minimization has finished running, and this graph looks nice. As expected, bond energy should ideally reduce, which is great. And let's just see the Leonard Jones short range graph. Okay, this is fairly interesting. It has stabilized somewhere around here. That's fine. So let's go to the next step, which will run NVT. I won't modify most of the parameters for NVT. I think that's completely fine. We run this. Yes, I'm completely fine with this. Okay, excellent. Looks like NVT is also done processing. This will help stabilize the system further. Right, let's just check the kinetic energy. Okay, all of this looks good. Let's just check the pressure. It should be ideally stable. Yeah, that's also fine. Okay, perfect. So let's go to the next step, which will be NPT. This will be the final step in stabilizing the system. And again, I won't modify most of the parameters here. Let me just click run. Okay, perfect. So NPT is also done now. Uh, and let's just see the Leonard Jones short range for this. Okay, this is fairly fine. And the position restraints are also stabilized. Perfect. So we'll go to the next step, which is the main step, which is production run. And so in this step is where we'll actually figure out, let me hide water, if the protein area, which is the terminal area, which was fairly low in the model confidence, right? If it modifies itself and if it is fairly unstable under molecular dynamics. So I'm going to perform a molecular dynamics simulation of let's say 50 nanoseconds. I think okay, just suppose still 50, which is fine. Um, so let me say instead of 50, 49 nanoseconds. That should be fine. And again, our pricing is fairly straightforward. 49 nanoseconds, 49 pounds. That's it. Right. So let me click on production run. So what's going to happen now is this is what I really love about MDSim 360, where the graphs have as the computation happen, all the important graphs for analysis, let's say radius of gyration, RMST, etc., they appear live, right? So first it takes about 5 to 10 minutes for the simulation to start, but once it does, all the graphs appear live. So as the computation happens, I can test if my theory is right. Do I really need to wait for 15 nanoseconds and then see the results? No, I can start analyzing the moment the simulation happens. So let me keep this to run, and I'll be back soon. Simulation has started, and as you can see, the results come live. So I'm going to click update graph, and this is the radius of gyration graph. Okay, And this is a very interesting graph. This is the most important graph for us right now, RMSF, right, which shows a lot of fluctuations towards the tail ends, right. See here. And because the simulation is just started, the remaining graphs don't make a lot of sense right now because it's only what 240 picoseconds, right? Let's so in the meantime, what we can also see is we can play the simulation, only 10 frames till now. Let me play. It gets over fairly fast, but that's okay. So we'll come back. We'll revisit this once the simulations have reached around, let's say, 25 nanoseconds midway, and then we can, revisit it again once it reaches the end. Great. See you then. Okay, great. So it seems our MD simulation has progressed to around 5 nanoseconds, 5 to 6 nanoseconds. So now I'm just going to click update viewer, which is going to load all the frames, and I'm going to click update graphs, which is going to load all the latest graphs. As you can see, it has loaded the latest graphs here, and it's going to do the same for all of the graphs. So this is what I mean by live graphs. And let's just check out the simulation. Let me click play. Perfect. So now as the simulation progresses, we are going to see the rest of the analysis also. We'll check back again for all the other graphs, how they have progressed uh, somewhere midway. Yeah. Okay, great. 10 hours later, the production run for 50 nanoseconds has completed, and let's just check it out. So let me play the trajectory first. So it has indeed gone through a lot of change, as you can see. The terminal end here, right, has changed dramatically. Let's just compare it with the first one. Yes, perfect. So these ends have changed completely, and uh, which sort of corroborates our findings, or at least helps, with our assumption. And now let's just check out the analysis graph. The radius of gyration is fairly okay. It's not changing continuously, and as expected, the RMSF has a lot of fluctuations towards the tail ends, but towards the center it is fairly stable, which is what we initially expected. Again, towards the tail end here, there's a lot of fluctuation. The intra-hydrogen bonds have increased over time, and the protein solvent bonds have reduced over time, which is expected, which means conversely the protein would have become a bit more stable because it's not creating a lot of bonds with the solvent, rather it is creating a lot of bonds with itself, which is what the intra-hydrogen bond depicts. Salt bridge analysis, okay, yeah. And which is a bit converse, because what is interesting is the protein internally is very compact, is more compact now, even though the terminal ends have fluctuated quite a bit, which means the total accessible area, solvent accessible surface area, which makes sense, has reduced completely. It has reduced quite dramatically. It started off with 130, and now it has slowly tapered down to 100. This also is in line with the protein solvent hydrogen bond analysis. So it seems that the protein has become more compact, and at the same time it has gone through a lot of fluctuations at the terminal ends by compressing itself internally. So Puffer, I think this mostly agrees with our hypothesis that when the pLDDT values from AlphaFold are low, that means we can see a lot of fluctuations and a lot of instability in those parts. But certain areas which have predicted high pLDDT, those areas will not have a lot of fluctuations at all. Rather, they will conserve their shape even further. Perfect. So for such analysis, try out MDSim 360. It's completely online. I could do this in a matter of minutes, literally, and I can quickly test out any hypothesis I have just by uh, uh, opening Google Chrome and running it online. See you in the next video. Thanks.